Our next speaker is actually coming to us from a different angle. Our next speaker is Professor Francis Bilson Darku from the University of Notre Dame. Francis got his PhD from my alma mater, actually, from University of Texas at Dallas in statistics. And since then, he has been working on applying new statistical and analytical techniques onto real-world data. And actually, I think we often forget, working in machine learning, that we hand machine learning models, the data, and they figure out the statistics and everything behind them. But statistics is really what we initially did to get that human knowledge in the first place, to get our foundations. So Francis is here to talk to us about how to leverage statistics in his applications, specifically in sequential analysis. Sorry. And how that applies in the industrial setting. So, thank you for coming out.
Thank you very much.
Yeah, I think we have there it is.
It is? Okay, good. Yeah, thank you very much. So as he said, I have my background in statistics, but I find myself in a business school, so I'm still working with business people. And I'll try to keep my talk in 5 minutes, plus or minus 10 minutes. That'll be fine, right?
I'd be very happy with minus.
I'll come back to that joke. All right. So I was very happy to be invited to give a talk here because of big data, people think everybody has data. Everybody think, oh, we have the data to do everything. But it's not the same for everybody, especially for young, new, or maybe fiscal-based companies, or even developing countries. Data is scarce, it's expensive to come by, and it's time-consuming to collect. So that is where my research area plays a big role. And as the talk says, it's applications of rule-based sequential procedures in industrial setting. So the outline of the talk, I'll just give you a brief history about how sequential analysis started, give you some common applications, then talk about one of my works, and then give you a general conclusion and some advantages of sequential analysis. So let's start with introduction and history. So I'm pretty sure I designed it with Microsoft in Windows, so I'm pretty sure some stuff would go wrong with Mac. So pardon me. So I said history, history. So let's talk about World War II. World War II wasn't a good time, but so many good things came out of it, especially in the field of statistics. There was push for new methods, push to validate production, to implement operations research, and that was a dawn of a lot of statistical methods. So one of the things that came out was sequential analysis. And how does sequential analysis play in World War II? In the midst of the war, new machinery, artilleries were produced, right? To fight the enemy, whoever you consider to be the enemy or friend, you need some tools. But we are in the middle of a war. We don't have time to take 100 samples and test that the artillery is working. We need the tool right now. So how can we guarantee that the production process is okay, the product came out very good, it's functional, and it can be deployed on the battlefield? How do we do that? You can't wait and produce 1,000 samples and test, and then go and report, oh, now we are ready. By the time you do that, the war will be over and you'll be the loser. But before then, Stewart, excuse me, I'm under the weather a bit. In 1931, Stewart introduced what you call the quality control, right? Quality control chart, where you monitor an operation system that is a system producing a product as is intended, right? So the production is going on, and you're monitoring it as the product comes out. For example, let's take filling a bottle of soda. You want 2 liters of Coke. Are you always filling the bottles with 2 liters? Or are you overfilling it, or you're underfilling it? Yes, there's going to be some variation, but is it cause for alarm? Is it filling it too much? So that is where quality control comes in, for you to check whether your system is in control or not. So this brought up the idea, can we bring this also into other kinds of production? So Abraham Wald, who was a Hungarian, and George Bernard introduced what you call sequential testing. Opposed to traditional hypothesis testing where you gather your data, you test, can we be testing whilst the production is going on? And say, oh, we can come to a conclusion, reject the null hypothesis. Or maybe do not reject the null hypothesis, right when the production is going on. Then further on, it was also introduced into estimation problems. Can we estimate the quantity we want, right? Is it the temperature we want? Is it the blood pressure of somebody who else you are measuring every day? Can we get to a point and say that we can make a conclusion, this is the average of whichever metric you are taking? So this brought up so many discussions about, is it really a good thing to be testing or estimating whilst you are collecting data? People started challenging this idea as opposed to the traditional way of having your data complete and then making your analysis or doing your regression or whatever you want to do. So Charles Steins and others then decided to develop a theoretical framework for sequential analysis, showing that this method works. This approach of looking at data collection and analysis is grounded in real statistics. So I've been giving you history. What is sequential analysis itself? The definition provided by Michael Barron, fun fact, he was my professor for probability theory. He's currently working at American University. He defines sequential analysis to be the concept of statistical estimation or decision making in real time as data is collected. So if you look at the definition and the examples I've given, then sequential analysis comes in when data is analyzed as they are collected. That is key, right? You don't wait till you finish collecting. As you are collecting, there's some background check to tell you whether you have enough or you should keep collecting data. This also implies that as opposed to traditional statistics, where our sample size n is fixed, we know the sample size. Here we don't know the sample size. The sample size is also a random variable that we are going to estimate at the end of the day. So you don't know your sample size, and it gives you some advantages that I'll discuss almost at the end. So the key thing here is, when do we stop sampling? That's the key thing in sequential analysis. So all sequential analysis has some kind of predefined stopping rule. That would tell you that you have enough data, go ahead and make your conclusions or do your analysis. That is the key thing in every sequential analysis. So in summary, you can define sequential analysis as learning and deciding as you go. So it's a continuous process. So when do we use it? And I think I've alluded to some already. When you don't have data in the first place, or data is limited and you are now collecting, you don't have to wait to collect all the data you want. As you are collecting, you can be doing analysis when you use sequential analysis. Another example is when the data itself arrives naturally. So as you are producing a product, you are manufacturing vehicle tires, or maybe car seats, you are actually producing it one at a time, right? And you are collecting data on them. So the data you are getting is coming sequentially, which lends itself to sequential analysis. And last but not the least, not last but one, in sequential analysis, you have more control over your precision because your sample size is not fixed. Immediately you fix your sample size, your precision is determined by the data you have. But if you allow your sample size to vary, you can fix your precision. Like, I want this precise measurement. So you can keep collecting data until your stopping rule tells you that you have enough, you are going to meet your precision level. So that's one advantage of using sequential analysis. Another good advantage is, if you need data, how much data do you need? Even if you say you want big data, how much is big data? Right? Maybe you have too much data and it's going to cost you. Data doesn't come cheap. It's expensive and it's time consuming. With sequential analysis, you can use the smallest possible sample size to achieve the same accuracy level that you want. And that saves you money and time. Another reason to use sequential analysis is when you have little to no prior knowledge about the parameters of the population, right? There's this field in statistics called power analysis, right? It helps you to determine the sample size so that you can achieve some accuracy level. But under that field, you need to have prior knowledge about the population. What if you have no expert knowledge? What if you haven't, this is a new field you're entering, or this is a new data you're collecting, you have no idea about what you're going to see. Therefore, you cannot even determine, I need 100 samples, or I need 30 participants for this experiment. So sequential analysis helps you to go through all these processes without much of a hassle. I mean, there's something you're going to give. So what are some of the common applications of sequential analysis? Okay, so stuff I'm missing. The first one is agriculture, which is very common in India. That is one big area where sequential analysis is thriving in India. It was first implemented in agriculture where farmers wanted to know the microorganisms in the soil. So you have a plot of land, let's say 1 acre of land. You want to know how many earthworms on average on this acre. You can't collect all the 1 acre of sand, right? You need to sample. But how much sample is needed? So sequential analysis was used to keep sampling until a point where their stopping rule told them, you have enough sample, the average microorganisms in the sample you have is enough, and it's a good estimate for the entire 1 acre. Another example is quality control that I've mentioned earlier on. You're producing a batch of goods. Initially, machines work very well, but with time, with heat, with pressure, they start to malfunction, right? At what point do you think the malfunctioning has set in? Right? Once in a while, there'll be a variation. Is it a cause for alarm? Or it's just a random event that happened? So sequential analysis helps you to determine that. And a very good place where sequential analysis will thrive in is biomedical and clinical trials. You know, getting data, getting people to do clinical trials is expensive. So how many people do you need to make sure that the efficacy of the drug can be determined? So here they set the efficacy of the drug, which would be the precision or the accuracy level they want. And then based on that, they keep sampling people until their stopping rule tells them that you have enough sample. And it doesn't have to be sequential, it can be in 2 batches, right? You do the first experiment, based on information you obtain from the first experiment, you can now update yourself and say, oh, based on this, I need 50 more people. Another application still in clinical trials is, well, let's say you have 2 drugs, right? The drug is already on the market and a new drug. How do you sample people into the 2 groups? Right, do you have to give it 50-50 equally? Are you getting the same information? So based on sometimes the variation in the results, you may have to allocate more people to one group than the other. And sequential analysis helps you to be able to determine how to apportion people to the group as the experiment goes on. Another example, which is the 4th one at the right bottom corner, is signal processing. For example, you have smoke detectors in the room, right? It's constantly sampling air samples to determine what is the CO2 level, or maybe what is any kind of air impurities that you're talking about. You need to determine as early as possible if there are some impurities that have exceeded some level, right? But at the same time, you don't want to give false alarm. If you keep giving false alarm, then nobody will pay attention to you when you're actually giving the right alarm. So sequential analysis would help these processes to balance out reducing false alarm, at the same time reducing delay time in detecting the right signals. 2 minutes. Okay. So there are some few branches. We have sequential hypothesis testing, which helps you to do hypothesis testing sequentially. We have change point detection, like signal processing, and we have sequential estimation, which is actually my area of research. So I'll give you an example of the work that I've done. I know with my co-authors, we were trying to estimate what we call effect sizes. So what are effect sizes? Effect size is any quantity that reflects a magnitude of some phenomenon. So anything you want to estimate, you can call it effect size. Common examples are coefficient of variation, regression coefficient, correlation coefficient, standardized mean difference, even R² from correlation is an effect size. So here, we gave a general class of effect sizes. Any effect size that can be written as a ratio of two functions, right? If you can write it in this way, you can apply the methods that we proposed. So an example is standardized mean difference. For example, what is the difference in treatment effect for two drugs, right? How do we estimate this? First, you need to get what you call a point estimate. But in practice, point estimates are always not the same as the true values. So most of the times, you are encouraged to add confidence intervals. Confidence intervals will tell you how precise your estimate is. If your confidence interval is too wide, like I gave at the beginning of my talk, I will talk for average 5 minutes plus or minus 10 minutes. That is a wide interval, right? It's not meaningful. So how can we give an estimate that is narrow without making so many assumptions? How can I guarantee that at the end of the analysis I'm going to do, my confidence interval will be narrow? You cannot guarantee this if you have a fixed sample size. So to do that, you have to lend yourself to sequential analysis. So let's take, for example, I have an estimate Tn, don't worry about what it means. Tn estimates my effect size, right? And the confidence interval is given us, as you can see below. This is your point estimate plus or minus a margin of error. We could have computed the sample size if we know the variance of our estimate. What if you don't know? What if you don't know? You need to collect your data to estimate, but you don't have the data. How do you estimate? So you are left in this conundrum. But to be able to do this, that is where we also come in. So in our paper, what we did was, it's very simple. Choose your confidence level, right? Choose how wide your confidence interval you want it to be. These are the only two things you need. Then first, our procedure will tell you the pilot sample size. What do you need initially? So you collect your pilot sample, then you estimate your variance from the pilot sample. The formula of the variance is in the paper. I don't want to bore anybody. Then you keep collecting data and checking if the stopping rule is met. So when this stopping rule is met, it means you have enough data. Go ahead, construct a confidence interval, and your interval will have a narrow width as you want. So this is just an example. We have several works that I can refer people to who are interested. So in summary, what are some of the advantages of sequential analysis? For example, hypothesis testing, traditionally if you took any stats class, your professor would tell you that you never accept the null hypothesis. You can reject or fail to reject. You never accept. But with sequential analysis, you can reject the null hypothesis because you can set the type 1 error rate, which is false positive rate, and set the false negative rate that you want. When you fix these two, you can always reject the null or accept the null. That's one power of sequential analysis. And I've talked about confidence intervals. You can control how wide the confidence interval will be. You can also do hypothesis testing with a smaller sample size as opposed to using a fixed sample size approach. And lastly, you don't need to make several assumptions. You can always learn from your data as you collect them. So remarks, it's easy to implement. All you need is a stopping rule. And it's appealing to so many areas where data is expensive, where agent precision is needed, where data is being collected sequentially. And the difficult part is that it needs a lot of theoretical foundations. All right, you can't just stand up and do any sequential analysis you want. You need to show that, yes, the method works, the method is better than a fixed sample size approach, and eventually you have to stop. You have to show that, is this process going to stop at some point? Is this process going to detect or estimate whatever I want appropriately? So this is the difficult part of the research work, but aside that, it's really easy to implement in the real world. So thank you, and anybody who wants to reach me, that's my email address, and I'm open for some questions.
Thank you so much, Francis. So any questions?
Right here.
I'll give you the mic
That's a
myself.
great talk, Francis. Question for you. I'm curious how you see this being applied in sort of like the field of AI, and where do you see this type of, with its knowledge, or this is a great idea, by the way.
Yeah, so when it comes to, as I mentioned some earlier on, when it comes to signal processing, it's actually being applied. When it comes to production quality control, it's highly being applied. When it comes to medicine, they actually use it because data is expensive. But with the field of AI, if you talk to, as I said, those with big data, they don't see why sequential because they think they have the big data. But in the physical world industries, one way to apply this is to use it, especially in the initial stages, right? When you start a process where you don't have the data, and especially when you don't have the expertise. Right? If you can use sequential analysis as in implement any of these procedures, and I'm by no means an expert in sequential analysis, right? I deal with estimation. Some deal with hypothesis testing. You have two products, right? You want to put the two products on the market and see which one is okay, which one would people buy into it. Sequential analysis will help you, right? As a product on the market, getting feedback, at some point you can determine which one is okay without keeping both on the market for too long. Does that answer your question?
That's fine.
Compliments for giving a talk on sequential analysis without saying the word Bayes. That was very, very brave. I'd like to give an example in totally different terminology, but Microsoft published information about one of their ad targeting algorithms, which used Thompson sampling to determine how to estimate parameters. It was sequential analysis in drag. So it's been used for sure in this.
Thank you very much for that comment.
Oh, thanks for the extra data.
One more way for question. So, yeah, thank you for your talk. But have you do any like the comparison or the evaluation between, even though with the small data, with your sequential analysis and the pure ML?
I mean, when you say ML is a big word,
Uh-huh.
but in all of our publications, we need to do some, one, we do simulation studies, right, to show that the algorithm works. Then we do some applications also to show it. One thing that I didn't mention was, I have one work that I published, I think in 2000, which was, if you have a complex survey structure, right, for example, we did it with India. So India has a lot of states, and each state has a lot of districts. And if you want to do a sample survey, the states are kind of heterogeneous, right? But within a district, there's homogeneity. So how do you select districts among different states such that at the end of the day, your overall estimate is a good representation of the country? So in that paper, we did simulation studies, and then we use data from India to show that using our method, you will actually sample fewer households than using a fixed sample size approach. And you get the same result.
I'm going to zoom on here.
Okay, thanks. We have time for one last question in the back there.
Can you switch
for this to work, do you have to assume stationality?
Do we have to assume stationarity? It depends on, as I said, there are different branches. So it depends on the branch that you are working with and the assumptions underlying your method, right? If you are dealing with, let's say, signal processing, depending on the method, you might have to assume stationarity or non-stationarity. That is, it's not my field. If you are dealing with hypothesis testing, what you are going to assume basically is that the underlying mechanism of the data doesn't change within that short period of time you are sampling. The same goes for estimation. We assume that the underlying mechanism doesn't really change in that short period. And it's a practical assumption to make because when you're collecting data, you pick them one at a time, right? Unless the data is sitting there, but if you are getting new data, definitely it comes in one at a time. Maybe in a short period, but it's still one at a time.
Okay. Thank you so much.
Thank you.
That was such a great talk.